Hello everyone, this is Elijah Moretsky bringing you today a Quaternion visualization that I found personally helpful in understanding how Quaternions interact with each other. If you only want to see the visualization itself, you can skip to the link in the description. If you want to understand how this visualization is generated, I'll be talking about that for the first several minutes. It will require some understanding of what Quaternions are. There's a great video by 3 Blue, 1 Brown, also linked down in the description. If you want to have a full understanding of how this works, I recommend watching that first. And without further ado, let's get started. So here's the stage. It shows the equation depicted in the top right. The x-axis is representable by the variable x. What you're seeing now is an invariant equation. So it's completely flat and there's no change in time. So when we add a sine wave to the real components of the Quaternion, you see that it oscillates vertically. Now let's see what happens if we add a sinusoid to the I component of the Quaternion. Something similar happens with the J component. You can see it's oscillating through magenta and white instead of blue and white, and pretty much the same effect with the K component. So now let's try doing it with all 3 imaginary components of the Quaternion. You can see it ends up oscillating through all the colors, every single hue. Occasionally it ends up going white. That's due to the imaginary components all being equal, so they end up adding up to white. So that was not very interesting. Everything is pretty uniform across the x-axis. Now let's look at a bit more complicated of an example. We're going to take this 1/2 plus I plus j and then multiply it by a rotation versor. That rotation versor is essentially a Quaternion of norm 1, and what happens when you multiply a Quaternion by a versor is it rotates it around that Quaternion direction. If you notice, we're raising that rotation versor to the power of x, so what's going to end up happening is we should see some rotations around the x-axis. And sure enough, there's no sine waves at all in these equations, yet we see oscillations both in the color and in the magnitude. So now let's try adding a sinusoid to the K component of the rotation versor. Notice how it eventually completely flattens out. That's due to the versor not having any imaginary components. It ends up just doing 1 to the power of x, which will always be 1. That's why it ends up going flat at some point. So essentially, the larger the imaginary component, the more oscillations you'll end up with in this visualization. Now let's try adding a sinusoid on the magnitude. Now we want to see what happens if we rotate the I and J components of the core Quaternion. We want to have these at a magnitude of 1 all the time. Similar with complex numbers, if you have the sine of one and the cosine of the other, you'll end up with a magnitude of 1. Show you a quick proof of that. So we're going to do sine t of I plus cos t of j. We're going to expand that out by squaring it. And then in the top right, you'll see the Quaternion identities. So ij is going to end up as negative ji. So that entire middle section of this expanded equation is going to cancel itself out. Simplifying, plugging in the I squared and j squared, we'll see that the entire equation is equal to -1. And the magnitude of -1, of course, is 1. So there's the proof that sine t of I plus cos t of j is going to be 1. So we shouldn't see any oscillations in the magnitude. And sure enough, we only see oscillations in the colors. We don't see any change in the magnitude. So let's put it all together. Here's the oscillating magnitude and the oscillating colors and the oscillating distance between the crests. Here's another visualization of some pretty simple function. You are oscillating the magnitude with time and then applying a oscillation to the imaginary component. So you end up with this spiking behavior. And hopefully, if you understand the previous example, you'll see why this is happening with this equation. So as a recap, here are the three equations and their visualizations. We want to combine them somehow. So the first idea we can have is to add them. But that's going to end up being very predictable, since each of these is a periodic function with a short time span. And that's no fun. So instead, let's add the second two equations and multiply by the first equation, which is the color oscillations, to the power of some time-dependent variable. In this case, I have denominators of all the times divided by prime numbers, so it will end up being very unpredictable. For the rest of the video, there's 25 minutes of footage with some nice soothing music. I'll put some links in the description to parts that I find interesting, and enjoy!